My name is Sami Khairy and I'm a research aide with Prasanna Balaprakas in Argonne. The title of my talk is Reinforcement Learning. I'm going to give you a quick reinforcement learning tutorial. The outline of my talk is as follows. I will start by giving you a brief introduction to reinforcement learning, the basic ideas and the jargons that we use in this field. Next, we are going to discuss on-policy versus off-policy learning approaches, and then we are going to go through 3 of the basic algorithms in RL, and I have implemented those in a Jupyter notebook, which we will go over to see how we can use these algorithms to solve a simple classic control problems. So let's get started. So what is reinforcement learning? In a nutshell, it is a branch of machine learning which attempts to formalize the notion of learning in human beings. So the word reinforcement comes to us from behavioral psychology, where it describes a technique by which it incentivizes an individual to do or produce good behavior. In our machine learning framework, we have an autonomous agent which learns to map situations or states to action in an interactive fashion and by repeated interaction with the environment. The environment gives the agent a reward signal to guide the learning process. Based on the reward signal, the agent either reinforces the action because it produced a good reward, it was a good action, or it will avoid this action at future encounters because this reward was probably bad or it resulted in a penalty. So having that said, the objective here is how to maximize the collected rewards over time. Mathematically speaking, a reinforcement learning problem is modeled as a Markov decision process, which is a classical formalization of sequential decision making. We have a state space S and an action space A, and we have a stochastic transition function that maps from a pair of state actions into the next states and a given reward. So the rewards here are stochastic and the transitions are stochastic. It is called a Markov decision process because the transition probabilities are independent of the history. It only depends on your present. This is important to note when you start working in this field. If you do not stick to this Markovian property, your policy that you will learn or your algorithm will probably fail. So at each time step, the agent will observe its state. So here we have a simple 3-state Markov decision process. Based on the state, it will take an action. For example, it can take a 0 or a 1, and this will send the agent to another state probabilistically. The reward it receives is also probabilistic. It can receive a reward that is positive or negative or not receive a reward at all. So this forms what we call a trajectory, which is a pairs of state action reward that goes on from the starting time step until a cutoff time, big T, which we call the episode length. So if we have a finite Markov decision process, this is going to be finite up to time t. If we have an infinite Markov decision process, this goes on and on forever. And in that case, we probably need to do some more tricks to make the math works. So what is the objective here? As I mentioned in the previous slide, we would like to maximize the collected rewards over time by choosing a policy or a strategy that if we follow and we are choosing actions in each of our states that are producing good rewards. So let's define our return at the time step t. It's a summation of the reward you get immediately and all future rewards. If this is a finite horizon MDP, then we are good to go because the summation will be bounded because there's a cutoff trajectory there's a cutoff point in the future. However, if we have an infinite Markov decision process and we are going to simulate this infinite interaction, we need to make sure this summation is bounded, and here we introduce a discount factor, gamma, to make sure the summation is bounded. This is not the only reason why we include the discount factor. The other reason is it basically trades off how far or short-sighted the reinforcement learning agent is with respect to taking action at the current step. So agent might take a step that might take an action at the current step that is not necessarily producing the highest immediate reward, but that will put their agent on a path or a trajectory to victory and producing much higher rewards later on. So in model free reinforcement learning as opposed to model-based reinforcement learning, the transition probabilities or the stochastic function that maps out every pair of state actions to a new state and reward is not known. Having that said, how can we solve this problem? Before we get to that point, let's talk about some RL jargons that we need to be familiar with before we start looking into any of the reinforcement learning algorithm. First, we have something called a policy, which is basically a stochastic map from our action space to our state space. And that's basically what we are trying to solve for in order to maximize our collected rewards over time. The other thing we have here is the state value function, and this is defined for every state in our state space and for a given policy. It basically describes what is the expected total rewards that the agent is expected to have if it starts at state S and continues thereafter following the policy pi. And another important function is called the action value function, which is sometimes referred to as Q function, and this is defined for every pair of states and actions. And it describes how much the total expected rewards is going to be if the agent starts in a state S, takes action A, and follows the policy pi thereafter. We say a policy is optimal if and only if the value of a state for all states under this policy is better than any other policy there exists in the policy search space. If the agent learns the optimal policy, if the agent learns the optimal value function or the state action value function, then we are able to rederive the optimal policy. How is that? For example, if we have access to the optimal state action value function, we basically look at whatever actions are available at that state and we pick the one with the highest Q function or Q value. If we have access to the optimal state value function, how can we derive the optimal policy? In that case, we need to look at the Bellman optimality equation and choose the action which satisfies this equality. Okay, so now the question is, to learn the policy, we have to learn the optimal value, state value function or state action value functions. How we do that? So to address this question, there are two important points that we need to address first. Given that we do not know the transition dynamics, we need to do enough exploration in our search space for the policies in order to do well. You cannot get many rewards or you cannot get higher expectation if you don't do proper exploration of your search space. So here we have a trade-off between exploitation, which is taking actions based on our previous experience, and exploration, which is trying new actions for the sake of exploring new trajectories. The second thing that we need to address is, okay, so we have done our exploration, so how can we learn the value of a state or the state action value of a state action pair? So for that, we need to have a way or a mechanism to estimate those functions based on interaction with the environment, and that's what we use temporal difference learning for. Let's get started with off-policy versus on-policy learning approaches. So in order to trade off between exploitation and exploration, there are two different approaches, broadly speaking. The first one is called OnPolicy approach, and here we are evaluating and improving the policy that we are using to generate the actions. So, and given that we are using the policy that is most updated, this means that we are throwing away past samples or past interactions with the environment. This means this category or this approach is not sample efficient, but however, this is more stable because we are optimizing what we care for. We are directly optimizing the, for example, average rate of returns. Some of the algorithms, famous algorithms that fall under this approach are the VPG, the vanilla policy gradient, the RPO, trusted region policy optimization, and proximal policy optimization. In the other approach, we are using two different policies, one to generate actions, which is called the behavior policy, and the other one is called target policy, which is which is the one we are optimizing for. So because we are using an off-policy approach, we can reuse our past experience, we can reuse our past samples that we have collected so far in order to optimize our current policy. However, this is more sample efficient compared to on-policy approaches. However, there are no performance guarantees that this will do well. Empirically, we can get good performance. However, there are no guarantees. Why? Because we are indirectly optimizing for what we care for, and this algorithm, what are doing is basically making sure the agent is self-consistent with the Bellman principle of optimality. Having that said, we need some strategies to explore our search space. So what are basic exploration strategies that we have in free reinforcement learning? The first one is called exploring starts, and here in every episode, if we have a finite horizon MDP, we start from a different state action pair. Epsilon greedy is basically you are choosing with probability epsilon a very random action. However, with 1 minus epsilon, you are choosing the optimal action based on your experience. And there is another one, it's called the Boltzmann approach, which is we start with a soft stochastic policy. We're having a non-zero probability of choosing any action in any state, and we gradually move towards a deterministic optimal policy. So now we are going to talk about the temporal difference policy evaluation, and here what we have is we have come up with some policy or strategy to choose actions. So how can we tell what is the quality of this policy? So in order to do that, we need to learn or estimate the state value function or state action value function. One way to do that is to keep a running estimate of your value or state value function. Basically, you randomly initialize your state value function to random parameters, or you could even start from zeros, and then you take an action based on the policy you suspect to be good, and then you get a return, and that's the update rule that you use to estimate your state value function. It's basically a running estimate. We have this recursive formula that governs the value of a state with a successor states, and that's something we can derive based on the Bellman equation. The terms in between the brackets are called the temporal difference error. If this goes to 0, this means we have converged to the true state value function that governs our policy. And at convergence, we have this recursive relationship between the current state value and the value of its successor states. Alpha is just a step size parameter. It's called the learning rate, and we can decrease it throughout training. So let's talk about the first very classic reinforcement learning algorithm. It's called the QLearning. Here, instead of learning the state value function, we are learning the state action value function. So we have theoretical guarantees that this will converge to the optimal policy if some conditions are met. These conditions are basically: 1, we need to make sure that all state action pairs are continually visited and updated throughout training. The second condition is that we need to make sure that our policy is being greedy with respect to our Q function in the limit. That means that we stop having exploration in the limit. So this is the update rule for the QLearning. It's basically mimicking the update rule in the previous slide. One thing to note here is that the value of the next state is given by this gamma max A or QST plus 1A. So this is independent of whatever policy you are choosing. You are just being greedy with respect to your policy. When this converges, we have this equality here between QST and AT, and these terms RT plus gamma max. And this basically satisfies the Bellman principle of optimality, and this is why we are being self-consistent with this principle if we are learning in this approach. What is the problem with this approach? First, if the state space is very large, so here we are considering discrete state space because QLearning is tabular. You just populate a Q table. If it's very large, then this will require a huge amount of memory. The second thing, it does not work for continuous state spaces. One workaround is to discretize your space state, of course, but that's not efficient. So what do we do here is to maintain this state action value function as a parameterized function in the state space. And by doing that, we can reuse the techniques from supervised learning, which we know well, for example, neural networks or regressions to fit this function. So this is the basic idea of deep Q networks. It's primarily for discrete action spaces. Our state space can be discrete or continuous. It was, I think, proposed in 2013 or 2014, and it was a breakthrough at that time. What is very special about this algorithm? First, it uses a deep neural network or convolutional neural network to estimate or fit the Q state action value function. However, it's not as that simple. Why? Because when you have a supervised learning problem and you are trying to learn a mapping from your feature space to your latent space, then we assume that our samples are independent and identically distributed. This is not the case, however, in reinforcement learning because our samples are temporally correlated. The agent is interacting with the environment in a series of action-reward exchanges, so they are temporally correlated. So this leads the learning to diverge. What is the solution? Well, that's what DQN is about. We introduce something we call an experience replay buffer in which we store our interactions with the environment, and then when it's time to update our Q value or a Q function or fit our Q function to our samples, we randomly sample from this experience replay buffer, and this basically gives us better performance because we are somehow making sure that the samples are less independent of each other. Another important point that DQN does is having two separate neural networks for the Q function. So let's to see why this is the case. Let's look at the previous slide. So here we are taking the old value. We are taking the old value and adding some temporal difference estimation error, and then we're updating the value. So this means that as opposed to doing this in a table where you can just do this by replacement, when you are fitting a neural network, this means you are reading for a value from your neural network and then you are trying to fit a new value. So this can cause the network to diverge. So what DQN does is basically maintaining two Q networks, and then every some number of iterations we synchronize them. This is like it's like a hard way of maintaining the synchronization. The other way is just to average them every number of steps so that they are synchronized. So the last line of algorithms in reinforcement learning is the policy gradient methods. So this is different from previous approaches in the sense that here we maintain a parameterized form of our policy, which is our map from the action space to the state space. And then we define an objective function, and this is like a whole line of research, how to define the proper objective function that if we do gradient optimization on, we are learning an optimal policy. This is basically the high-level introduction to reinforcement learning. I have prepared a Jupyter notebook with the implementation of these three algorithms to see how we can use them to solve a very classic control problem. So let's switch to Jupyter notebooks for now. And you can find it under the reinforcement learning in the GitHub repository. And the title of this is RL_cart_poll. So the control problem that we are going to solve is called the cart poll. And let's see what is the description of this problem. So we have a pole that is attached by an unactuated joint to a cart. The pole starts in an upright position. The cart goes left and right by applying a force +1 or -1, and we need to make sure this stays upright as much as possible. For every time step that elapses and we have still an upright pole, we get a reward of 1. If it goes more than 25 degrees, then we lose and the episode is terminated, and we receive a reward of -1. Okay, so I've run this before, but probably it has restarted. So basically, we first import our packages, TensorFlow, Gym environment, which is basically providing you of a lot of environments to test your reinforcement learning algorithms on. To create an environment, you use this simple function, just gym.make, and you choose the string that describes your problem. If you check the help page for this, you will see what is our observation space, our state space, and our action space. So for this problem here, where is it? So the observation space is a 4-dimensional vector in R4, which is basically describing the cart position, the cart velocity, the pole angle, and the pole velocity at the tip. And our action space is discrete. We either choose 0, and this means we are going left, or we choose 1, which means the cart is going right. And by finding an optimal policy that maps this state space into an action space, we need to make sure the pole stays upright. The reward, as I mentioned before, is +1 for every time step that elapses and the pole is upright. So the very naive thing to do here is to do a random action selection, which is basically at each time step you choose a random action with probability 50%, you choose 0 or choose 1, and you can test this policy. It is a valid policy, and we can see its performance here. So I gave all of the reinforcement learning algorithms that we have here in this Jupyter Notebooks 200 episodes, and we try to maximize the number of time steps per episode, or the collected rewards in each return. So the random policy gives us 22 points. Basically, we can maintain this for 22 unit times. We can maintain the pole upright. The second algorithm, or the first reinforcement learning algorithm, which is the tabular QLearning, we have a catch here, is that this is only meant for discrete action space, which is okay for our problem, but also we need to have a discrete state space. So what can we do? Well, okay, we can discretize our state space. Okay, given that our state space is a 4-dimensional vector in R4, it's very hard to discretize, so I just do a heuristic trick by mapping this mapping this space using a tan hyperbolic function into the range -1 and 1, and then I can apply a 0.1 step-size discretization scheme. So these are the functions which basically take the continuous state space and produces a multidimensional vector that describes the state we are in, and then in order to avoid working with multidimensional NumPy arrays, I just convert this into a linear index. We have the step size 0.1, and the algorithm works like this. For every time step, we either select an action at random with probability epsilon, or we use the one which has the maximum Q value. So at state S, we see which action has the biggest or highest return, and we take this action. I start with a high epsilon, and over time I decay it so that I make sure in the limit I'm not doing any exploration, and I'm only doing actions based on my experience. So the update rule is basically the same as the one I have in the slides, which is the temporal difference estimation error. I launched this for 2,000 episodes, and I tested for 200 episodes and see how it performs. So here we can see that it performs better than a random policy, but not that great. We are able to maintain the pole upright for 67 unit times. The next algorithm is the DQN. So here we have two important parts. First is the experience replay buffer, and to use that we use this deck, which is basically a stack. Whenever it's full, we pop from the left, and the new samples are appended to the right. I have these hyperparameters. I describe my Q network by using these two hidden layers. I have two hidden layers of 24 neurons in each layer. I describe my placeholders for my actions, and for Y input. Y input is basically the discounted reward that I get. The loss is basically the mean squared error between the actual discounted returns that we got and the ones that are predicted from our Q network. So this is very analogous to regression problems in neural networks. We run the algorithm in the same fashion. If we take steps in our we take steps in each episode, and if we have a terminal, we just reset everything. We decay. We have an epsilon greedy exploration strategy. With probability epsilon, you select an action at random. Otherwise, you are using your experience. One important thing to note here is that we are doing this update through based on sampling from your experience replay buffer. The updates are basically also similar to the QLearning update, but we have a discounted reward for your rewards. I run this for also 2,000 episodes, and then I test it for 200 episodes, and we can see that it performs much better than the QLearning, where we have discretized the state space. We are able to maintain the pole upright for about 180 time units. So the last one is the simple policy gradient. Let's see what this is about. We define our observation placeholder, which is our state space, state placeholder. We have one hidden layer of 24 neurons. We have the probability of selecting either of the actions. So because we have two discrete actions, we use this sigmoid activation function. So with probability, if the probability is higher than 50%, you choose one of the actions, and the other way you choose the other actions. We have one thing to note here is the loss function. The loss function is basically we are reducing the log likelihood of our policy times the advantage. The advantage is basically our normalized rewards, discounted rewards. We normalize them to be unit variance and zero mean. This helps the algorithm to converge faster and has less variance in the learning process. And we minimize this using so this log likelihood function is very similar to the one we use in binary classification when we train neural networks. This function is basically used to discount our rewards. That's basically how we associate every step with the reward it got immediately and the one we got in the future. The training is also done in the similar fashion. We start by taking actions and interacting with the environment, gym environment using the step function here. After some number of batches, like the interactions with the environment, we do the update rule by optimizing our log loss likelihood function by doing gradient optimization. Lastly, I've also trained this for 200 episodes, and I run it for 200 episodes for testing. And the expected episode length and the expected returns are 276, so it does much better than DQN. These results are all sensitive to your hyperparameter choice and the choice of your architecture for the neural network. But it is known that policy gradient methods are more stable and are better than off-policy approaches. We have theoretical guarantees that will guarantee that in the limit you are reaching a good policy. So that's all for me today. If you have any questions, I'd be happy to take.
So if you're using reinforcement learning to do some sort of optimization, how does it differ from like the optimization that we talked about, say with Bethany? Like if you know that you're trying to use reinforcement learning on some sort of space that you might be able to say is differentiable, like why would you choose this over something like gradient-based?
Okay, so that's a good question. The question was how this reinforcement learning framework differs from unconstrained continuous optimization, let's say, right? So here we are searching for a series of solutions to a problem. We are not solving for one solution. So we have a trajectory through our Markov decision process. At each time step, we need to take a decision, and we are solving for an optimal policy at each time step. Whereas in optimization, you are just looking for that vector that will satisfy your constraints and have your higher objective value. However, you can still formulate a normal optimization problem as a reinforcement learning problem, and that's a project I've been working on at Argonne. In that case, you need to have a reformulation of your optimization problem to make sure you have this MDP formulation, and you can still do it.
So you're saying that like if you know that whatever you're trying, like if you know that your decisions for optimizing might change over time, that this would work better for that because your solution might change with each time step?
At each time step, we have a different solution for what we need to do.
So you could also do that with just a regular like with some sort of optimization. You just do it each time step.
So it's different. And in optimization, we have iterative algorithms that by using a gradient descent or Newton's method, right? So we are just looking for one solution that optimizes this function, right? Here we are looking for a sequence of solutions given different states that optimize the overall objective, which is the total expected returns. So it's a different formulation. We still have optimization here to solve for this optimal policy, but the thing we're looking for is a policy that maps our state space to an action space. In optimization, we can think of it as a bandit problem. We only have a stateless formulation, and we just need to take an action that optimizes the objective value. Does that answer your question?
Well, we can talk a little bit after.
Okay.
I think I might just be doing it differently than.
Yeah, sure.
Okay, cool, thanks.
Any other question?
Does this count for delayed reward in some implicit way?
Yes, it does, and that's why we have a discount factor. It's basically how to distribute your rewards that you get at the end of the episode or later on, and how much these rewards affect your current action. I mean, how much they relate to your current action.
So you did mention that the Markovian assumption is critical. So
Right.
So let's say for physics problem, right? I mean, most of them are not Markovian. At least ones I am aware of. So how do you deal with non-Markovianness with reinforcement learning?
Okay, that's also a good question. The question is how we deal with the non-Markovianness of a problem and make it Markovian. You can reformulate your state space by including more history points to make it Markovian, right? Basically, if you think your state space needs to have L times in the history, you include that in your state formulation to make things Markovian. You can.
There's no algorithm as such. On the algorithmic side, it still always has to be Markovian. There's no.
If you need to have good performance, you need to have the Markovian property. So in the recent project I was working on, my reward function was not Markovian. I was still learning something, but it was not that great. When I changed the reward function to be Markovian, things got much better.
So you have to find a reward function that's Markovian.
Reward function and also the formulation itself has to be.
So even though the system is not Markovian, you find a formulation that's Markovian.
Yeah, you can have an embedded Markov chain or Markov decision process that describes your system, and you can make it Markovian. I mean, at some point you can truncate it and make it much more Markovian than the original case, right? Another thing to note here is, I forgot what I want to say. Yeah, basically that's it. Okay.